Okay, this is our final video on proof by induction, and this is the proof of the Moivres theorem by proof by induction. So what we want to look at proving is that cos theta plus I sine theta all to the power of n is equal to cos n theta plus I sine n theta. Now our steps are the same as our previous proof by inductions. So step 1 is going to be prove true for n equals 1. So we start off on the left hand side, we're going to replace the n with a 1. So we're looking at cos theta plus I sine theta to the power of 1. And that should be equal to cos of 1 theta plus I sine 1 theta. Cos theta plus I sine theta to the power of 1 is just itself. So we're looking at cos theta plus I sine theta on the left hand side, cos theta plus I sine theta on the right hand side. Therefore, because the left hand side is equal to the right hand side, it is true for n equals 1. So that's our step 1. Step 2, we want to assume true for n equals k. So we're going to replace our n with a k this time, and we're going to assume that cos theta plus I sine theta all to the power of k does in fact equal cos k theta plus I sine k theta. So that is assumed to be true. Final step, we're going to prove true for n equals k plus 1. So our final step is to prove true. So we're going on the left hand side, we're going to look at cos theta plus I sine theta to the power of k plus 1. On the right hand side, cos of k plus 1 theta plus I sine k plus 1 theta. So we're going to work on manipulating this left hand side here to make sure that it looks like this right hand side here. All right, so I'm going to rub off my previous working out here now so that I have some room to maneuver. And we're going to look at proving this. We are going to need to use step 2, which is cos k theta plus I sine theta to the power of k is equal to cos k theta plus I sine k theta in terms of proving this. So I'm going to start off by writing this line up here at the top. So what we want to prove is that cos theta plus I sine theta to the power of k plus 1 is equal to cos of k plus 1 theta plus I sine k plus 1 theta. That's what we want to look at proving. Okay. All right, so let's look on our left hand side. The first thing we want to do is split and for the Moivres theorem, you just have to learn this process off. The first thing we want to do is look at splitting down our index. So we're looking at cos theta plus I sine theta to the power of 1 multiplied by cos theta plus I sine theta to the power of k. So we're looking at splitting our k plus 1 index into 1 and k. This part we've looked at in step 1, that is simply cos theta plus I sine theta. This we have assumed to be cos k theta plus I sine theta from sine k theta from step 2. So from step 2, we've assumed that this is equal to this. The next step is to multiply everything out. So we have cos theta multiplied by cos k theta. That's our first element. Next, cos theta by I sine cos theta by sine k theta. That's our second element. Next, we have I sine theta by cos k theta. So that's plus I sine theta cos k theta. And finally, I sine theta by I sine k theta is I squared sine theta sine k theta. Now, what we're going to do next is we're going to gather the real components of our expression together and the imaginary components of our expression together. So cos k theta is real, and because I squared can be replaced with a minus 1, this is also a real component. So let's concentrate on that first of all. So we have cos theta cos k theta. and I squared is minus 1, so that's minus sine theta sine k theta. Now, according to our trigonometric rules on page 14 of our log tables book, where we can see cos A cos B minus sine A sine B, that can be simplified to the cos of A plus B. So given that our A is theta, our B is k theta, we can rewrite that expression as cos of theta plus k theta. Factorizing out the theta, we're looking at cos of k plus 1 by theta. So that is the first part, first part of the right-hand side of our identity proven. All right, so that comes from the real components. Next, we're going to concentrate on the imaginary components. So we have I by cos theta sine k theta plus sine theta cos k theta. Again, from page 14 of the log tables, we're looking at cos A sine B plus sine A cos B, which can be written as the sine of A plus B. So given that identity, and again given that A is theta, B is k theta, we're looking at I times by the sine of theta plus k theta, which is I sine k plus 1 times by theta. So that's where our identities come from. So it's a bit mixed up. So this here in the middle will be our final line in our proof. This bit up here and down here is how we arrive at the cos of k plus 1 theta and sine of k plus 1 theta. So now, because our left-hand side is equal to our right-hand side, we simply have to write a final conclusion. So left-hand side equals right-hand side. Therefore, it is true for n equals k plus 1, provided true for n equals k and n equals 1, and therefore true for all n is an element of the natural numbers. And that is our final step. So in terms of de Moivre's theorem, step 1, prove true for n equals 1. Step 2, assume true for n equals k. And then for step 3, prove true for n equals k plus 1. This is your working out that you need to show. Again, it's just one that we have to learn off. It came up in the Leaving Cert in 2018. If you look at the 2018 exam paper, you can have a look at the marking scheme that was awarded for that. And that is the conclusion now of our proof by induction.